Okay, so here is the finished Variac, and I'm just gonna show you the features of it and the current settings and the trip time. So I've got a very light load connected to it, so I can show the low milliamps, and so I'll show you the features of it, and we'll do the test. So you put it on, and that's the booting up. Okay, and at the moment it's saved the last settings of the trip current, which is 1 amp, and I've got 100 milliseconds here. And so this is the reset button. So you press that to reset it. We have the ×2 for the time delay. So at the moment it's 100 milliseconds, and when you press the ×2 it will change to 200, so it doubles it, and it shows the cycles so the cycles for the 200 milliseconds. So go back to 100 and it's 5 cycles, because it's the formulas worked out under 50 Hertz. And so this yellow button here changes your scale. Okay, so for example, that's a manual. I'm changing the scale of the analog meter manually. And so if I've got it on the 0.5, which is the lowest scale, once it goes over 0.5, it will jump to 1 and to the 1 amp scale. And when the 1 amp scale has reached the limit, we'll jump to the second one. But if I set onto 1 now, so now I'm on the 1 amp scale, the scale is going to jump from 1 to 2.5. It will not go to 2 for the 0.5. So that's how I've done the software. And if I start at 2.5, it will jump from the 2.5 to 5 to 10. And when it comes back down, it will stay on the 2.5. And same thing, if I'm on the 5 amps, then it will stay on the 5 amps. So it's still auto, but it's gonna, if it goes past 5 amps, it jumps to 10. And then when you lower the current, it will go back to 5. And if I go to 10, now it will stay on 10. And it will not use these other scales. So I'm happy how I've done that. Let's go back to the 0.5. And then the other button is to whether I'm going to change the amps, trip time, or the time delay. So it's a toggle between the current and the time. So you can see now the arrow is on the time. That means I can change the time. If I press it again, it goes back to the current. So if I change the current, by the way, and the rotary encoder here, when you press it, it moves the cursor to the next step, and once it's in the end, then we'll start again. So it's only forward right. Okay, and so that's that. If I hold the button for 3 seconds, now it's going to show me the internal values of the frequency set, the microseconds, the period, what timer 2 is, PR2, and this actually is a voltage of the switches. So if I hold the cursor down, it's 2.6. If I press the amped time, it's 4 volts. If I press the auto scale switch, it's 2.2. So that's the internal values what the analog to digital converter is reading on the switches, because I'm only using one port one input IO input, and that reads 3 switches by having different voltages. So you hold it for 3 seconds again, and it goes back to normal. So here I have power on. Once it's tripped, it will trip. It will show tripped. So I've got a very light load on, and what I'm going to do, this it's a very light load. It can only draw 35 milliamps. So let's go and do 1 milliamp. So once I turn the voltage, and there's the current reading at the top left, it should trip around the 1 milliamp. Okay, so well, there you go. Maybe I turned it too quick. Redo it. So I'm putting up the voltage slowly. So it's reading 1. If I go a bit more, tripped. Now let's set it to 2 milliamps. Okay. Maybe I should bring this closer. Okay, so you can see it better. We'll turn the Variac slowly up, the voltage. 7 volts, so we're drawing 1 amp, 1 milliamp. Okay, and it should trip around the 2 milliamps. Okay, going up, 0.01 watt. Okay, it's flickering to the 2, a bit more, and it's tripped. So you see it's very accurate. I can set it from 1 milliamp onwards. Let's go to 3 milliamps. So I left the voltage as where it was, 17 volts, and it's reading the 2 milliamps of last. That's the current draw. Turn up a bit slowly. So we reached it, it's flicking to the 3. Okay, 25 volts, 0.07 watts. And there you go, tripped at 3 milliamps. Let's do a 4 milliamp test. So I've set the current settings for 4. Reset it, drawing the 3. That's what it tripped last time. That's what it's still reading. The current draw of the load. 28, 29 volts, 30 volts, 31.6, 32. It's flickering to 4. We go a bit more. Tripped at 4 milliamps. Pretty good. Okay, we go up to 5 milliamps. Reset it. 33 volts. We're drawing 34.4, 13 watts. Sorry, 0.13 watts. We're going up, 35 volts, 36, 38, and we're tripped. We hit the 5. So let's say if I press the trip setting, the reset, and I'm leaving the voltage with the load on and with the voltage where it was, we'll see what happens. And it trips, there you go. So it's tripping at 100 millisecond. Okay. So let's change the time delay. Now this should trip quicker. Well, it's probably because it's still trying to hit the limit. So if I turn up the voltage a little bit more, okay, I'll go a bit more. There you go. It's because the current is taking that little bit to reach. So I've put up the voltage more. So let's do a okay, I'm still in the time settings. Have it at 10 milliseconds. Change the time delay, the current now. Let's go to 10 milliamps. Okay, so I've got 10 milliamps, 10 milliseconds. Reset it, turn the voltage. Current's going up. 5, 6, 7, 8, 9. Let's see, it should trip around the 10 or just a bit more. We go up slowly. 10. Let's go a bit more. 0.81 watts, 0.82. There you go, tripped. It's pretty spot on, right? 10 milliamps tripping time. Tripping current. Press reset again. Okay, it will trip. It's hitting the 10 now. So now I go to 11, and when 11 milliamps, and when I reset it, it shouldn't trip. And there you go. It's drawing exactly 10 milliamps. So I got 1 more milliamp to go. I should trip. Turn the voltage slowly. I've hit the 11. A bit more. And it's tripped before it hit the 12. Press the reset, should trip. Okay, go up to 12 milliamps and it shouldn't trip. And there you can see it's not tripping. Okay, so I'll go a bit more with the voltage. It's flicking to 12. Okay, a bit more and it's tripped. So it's pretty good. Okay, now we'll do a high current test. So that was the low milliamp. So I started from 1 milliamp to 12 there, and now I'll change the load and we'll do a high current test. Okay, so now I set up a different load, and I also hooked up another current meter, an analog one, and it's on the 75 milliamp scale, and what it's reading now is around 5 milliamps, and my digital scale is reading 5 milliamps, and of course this one is not going to read anything because it doesn't go that low. So I've got it to trip to 100 milliamps. Okay, so we'll turn up the current. There it's reading around 31 milliamps, and you can see here the analog meter says 31 milliamps. Okay, and okay, so this meter it's saying 60 milliamps. Okay, my one is saying 62, and the reason is because it's running through another system where I've got another load that is measuring this. My unit is the total is the main source, but the current meter is not measuring the other load that I've got on. So let me pause it and change that and have it all in one. Okay, so I removed the light load that I had. That was the same load that I done the low milliamp test. So I disconnected that. So now we'll show that the current display is pretty much the same. So this one is saying around 6, and I'm reading about 6. Okay, going to 7. So there I'm reading 21 milliamps, and it's gone down to 20. So 20 milliamps, and that's saying 20 milliamps. There's the 20 there. So I'll go back to 60 now, and before I had 2 milliamp discrepancy because of the other extra load I had. Let's see if I could. So my current reading is 60 milliamps, and pretty much you can see there this one is reading a bit less. Maybe we gotta knock it a bit. These old analog meters. Okay, it's pretty much 60. So you see now pretty much 60 milliamps, and I'm reading 60 milliamps. Okay, let's change the scale on this. Okay, there it is there, 60 milliamps, and I've set it to set at trip at 100 milliamps. Okay, so 99. Now my analog meter started to read here as well. That's the 100 milliamp mark. We're reading 100, flickering a bit more, and it's stripped. Okay, 100 milliamps. Okay, let's go to 200 milliamps trip time. Okay, so we're reading 104. Okay, should trip around 200. This time we went a bit more. So here's where the deck, there you go, trip. Here's where the deck is a bit there's a bit of a difference there, where it's not accurate on all this, different voltage levels. Okay, let's go to 400. Okay, so you can see the scaling here. This meter's got a bit of static on it. Okay, it's very accurate. 203 milliamps, and that's reading 200 milliamps. Okay, and I've set it to trip at 400. So there's 300 milliamps, and also my other analog meter, which hooked up in series with the load, is saying it's 300 milliamps, and it should trip around the 400. Okay, and there you go, it's stripped. Reset it again. 397. It's going to hit the 400. Of course, the Variac, when I'm turning the dial, it's easy just to jump, 10 milliamps at once. There you go. See the voltage changing on the AC, and it tripped. Okay. Let's go to 600 milliamps. Reset it. And now you're going to see the auto scale change by itself. The analog meter changing the scale by itself once I go over the 500 milliamps. So okay, there you go. I go back down with the current, it changes scales again. Go up, changes the next scale. But just to show you, if I go on the manually onto the 1 amp. Sorry. Now when I lower it, it will not. Oh, it did. Let's try again now. Yeah, now it will stay on the 1. That's because I was drawing current while changing it. So now it stays on the 1 amp. Okay, if I go to the 2 amps, 2.5 amp scale, which I'm on now, it will stay on the 2.5. Okay, regarding, yeah. So go back to the 0.5, go again, change scales by itself. I've got it to trip at 600 milliamps. Okay, 570, 580, coming close, 592, 595, 6, 7, 600. There you go, and it's stripped. We'll redo it again. Press the button. Okay, there you go. 590 flickering, right? I go a bit more. Slowly. And it's stripped. Let's go to 700. Reset it. And it's stripped. Go again. There you go. I go a bit lower. 695. Go up slowly with the Variac. There you go. 701 milliamps, 700 milliamps. Let's go to 1 amps. You can see that where I haven't touched the here I haven't touched. I'm not touching the okay, just to show you what I was doing. I'm just turning up the voltage slowly. Okay, and I've got it set to trip at 1. Okay, 966, 970, 987, 9912, and it's stripped. Now let's set the current higher, and now I'll reset it and see what it actually was reading. And you can see once it settled, it was reading 1 amp, so that's why it tripped. Okay, so now it should change scale and trip at 1.1 amps. So I'm on the 2.5 scale, which is here, and I'm reading the top one here around the 1 amp mark, and at 1.1 it should trip. So 1.08, 1.09, and there you go, it's stripped. Anyway, I think that's pretty much the testing. And change the scale onto this. Go up with the current. Go to 2 amps. Reset it. Okay. I'm reading around 1 amp or 1.1, and the analog meter is saying 1.1 there. It's pretty spot on. And of course I've got the load here is getting hot. It's a resistor. So let me disconnect one part of the other load. By the way, the load, it's an element. So I just disconnected this resistor because it's got very hot. So that was in series with another element here, just to get better control with the Variac. Okay, so it's got too hot, disconnected that. Now it's the main element. Okay, so I've got it to trip at 2 amps. Okay, so I'm reading 0.6, my analog meter says 0.6, and the other analog meter is saying 0.6. Okay, we got 1 amp. My meter says 1 amp now because I've changed the scale. And it should trip around 2 amps. Actually, I'm not sure if this element can take 2 amps. Might not. So no, it can't. That's the full voltage now. I got 256 volts, 466 watts. So I cannot trip because the load's not big enough. So let's make it trip at 1.5 amps. Okay. Going up. Okay, now we're drawing 1 amp at 100 and, well, I've gone up to with the voltage 150 volts. It should trip at 1.5. The wattage is going up, 1.3 amps, 1.4, okay, 1.44, 146, 148, 149, 1.5, and there you go. It didn't go to 1.51, it tripped just a bit over 1.5. So it's good. So we'll do that test again just to see show you what I was doing here. Bring the voltage down, reset it. I'm putting up the voltage, okay. This is the last test. 1.48, 49. I'm going slowly. 1.5. Yeah, just over 1.5 amps, and it's tripped, so it's pretty good. So that concludes the Variac here and the testing of it. And yes, so thank you for watching that. Oh, and another thing I wanted to explain, and let me explain this, which I missed explaining in the first, when I explained the circuit diagram in the first place. When I talked about the toroidal precision transformer here to read the current, okay, which you got the primary going through the core here of the transformer, I talked about these burden resistors, right? And I said 1000 ohm 1K resistor, burden resistor to get the 1-to-1. And you probably noticed I've got 1.2K there, plus a 100 ohm resistor here. The reason why I done this here originally, in actual fact, you don't need this. You don't need this calibration here, and you don't need the 1.2. You can actually put just a 1K resistor here. In actual fact, in my first circuit, I never had this extra potentiometer here, variable potentiometer to adjust. I just had a 1K resistor across from the point to the ground, and that's fine. Then all you have to do is, which by the way, I did this circuit, how I said, was of a circuit examples of the net. I did add a gain pot resistor here, okay, a 25 turn variable resistor, to be able to have some gain here on the output. So if you put a 1K here, obviously we need to adjust this resistor here for the divide by 10 scale overall and total, and you would need to adjust the gain, right? Now I have the gain here, so technically I didn't need to have this pot here. And for anybody wondering why I'm using a 1.2 instead of a 1K, right? Or for example, 900 ohm plus the 100 gives you the 1K, is because what I found, some of these toroidal transformer, they could have slightly different windings, or the way it's been wound on the core will just give you a slight difference on the output, right? So, for example, if you change it, if you replace this, okay, you might need to readjust this there, either there or in the on the gain, on the output. But the reason why I done a 1.2, so that instead of 1000 ohm, I went 1200 ohm, for example, plus this resistor, is because when I measure with a true RMS meter here, let's say I've got 10 milliamps here on the primary, so I should have 10 millivolts on the 1-to-1 scale on the secondary. With a true RMS meter hooked up to this point, I found that it wasn't exactly here 10 millivolts. Now, how I said, even if it's not 10 millivolts, you can adjust the 10 millivolt on the gain on the output. So you get 10 millivolts here anyway. That's where in actual effect we do need the 10 millivolts. But for precision, I thought I wanted the input to be exactly the same as well. The input is calibrated as well, not just from the output. Are you with me? So I'm doing less modification on the gain of the output by having more precise input going on. Now, of course, the op-amps internally will change that anyway, and you still need to adjust the output. But again, in reality, I didn't really need this adjustment. Of course, you do need the divide by 10. That you always need this adjustment there, because we're calibrating this as a total, and you cannot be adjusting. If you adjust this for the divide by 10, then it's going to be out for the times 1. So you still need a calibration here, at least 1. But really, I didn't need this. But because I wanted to be fussy, if I hook up a true RMS meter, I wanted to read the exact input of the primary on the secondary there. That is why it ended up being a bit higher than 1K, because the transformer would probably still have some errors regarding the windings and the core. Okay, so I just wanted to add that I have encountered a problem with the SCR back-to-back, the thyristor. Not the driver, this is fine on the circuit board, but I have encountered a problem on the actual unit itself, and I will show a video on that, showing the waveform of the problem. Okay, so here I have fitted the SCR, the two SCRs back to back instead of the triac unit that I had, and the triac unit was actually this one here,
Okay, and I did encounter a problem with running this SCR onto the inductive load, which is the Variac transformer. And the problem that I encountered is that the SCR doesn't switch 100%. So I'm getting a voltage drop, and I'll show you that on the oscilloscope. It must be because of the back EMF affecting the gate circuit. I'm not exactly sure 100% to how you can solve it, because I've tried many things and I cannot really solve the issue. But I have improved it. And the improvement is by changing the resistor on the gates, on the gate circuit. And I'll show you that now. So the gate circuit here, it goes through this limiting 360 ohm resistor. So when it's switching one side of the gate, it goes through this diode here, through the triac, okay, and back to the it goes to the gate, sorry, there, and it's limiting. And when the other part of the wave comes from this way, that way, and goes to the gate that way. So what I had to do to improve the switching, because I hooked up a current meter here at the gate, and it's like drawing 14 milliamps, only 14 milliamps. And of course, once you start applying a load onto the transformer, then the switching comes better, and the current drops almost to nothing on the gate, because then the main current is being switched through the SCR. But I think what's happening is at no load on the Variac, because it's not really a load, the Variac, it's an inductive load, but it's creating back EMF. It's affecting where there's a voltage drop. It doesn't want to flow enough from there, and it starts flowing more through the gate, the current of the 15 milliamps. So what I did, I removed this resistor. I've tried lowering it, it was improving it up to the point where the current only goes, let's say, to 16 milliamps, just one more milliamp. That's when I shorted out. So when I remove this resistor, it draws an extra milliamp at no load on the transformer. And then once the load, you start putting a load on the inductive load, which is the Variac, then the current will drop pretty much to zero. So it doesn't like the way it is, because it's an inductive load. It's like there's not enough current through the gate to switch on the SCR properly, fully. So I'm getting like 10 volt RMS voltage drop, which it's causing a, if you hook up the Variac transformer to an isolation transformer, the isolation transformer starts to making a loud humming noise, because it's not, you got an oscillation. The voltage drop is actually an oscillation, 10 volt RMS. But I'll show you that on the oscilloscope. Okay, so what I did to show the issue, I hooked up the probes on the oscilloscope between the SCR switch, which is that point and that point. So I've got the ground point there of the probe, and the probe on the input, and that's the load side of the switching, right? Now I have to give a warning here that the only reason why I can do that is because I'm using an isolation transformer, which is isolating the earth. Because the probe on the oscilloscope, okay, the earth lead, the ground lead on the oscilloscope goes to earth. to the mains, okay? So otherwise I'll be creating a short circuit. So by having an isolation transformer before the Variac, then I can do what I'm doing. So do not apply, anybody attempt to do this test without using an isolation transformer supplying your Variac. Otherwise you'll have a direct short circuit and you blow up the damage the unit, or anything can, will have a big bang. So you don't want to be doing that without an isolation transformer. Okay, so now I turned the unit on, and it at the moment is on the it's been tripped, so the circuit breaker is off and the relay is off, and the probes are between the switching of the SCR, okay? And of course, because the SCR is off, okay, and I'm between the transformer and the input of the SCR on the other side, I'm measuring, it's like I have one to the neutral and one to the active. So you're seeing the AC waveform, and there's a bit of a distortion, and that's nothing to do with what I'm doing. This is a distortion on my mains on my property. So the wave, and you can see there, it's got a bit of a delay at the peak, which is not a good thing. But that's the electrical companies now. I'm not sure exactly what they're doing, whether this have to do with all the inverters on the houses having solar cells, and yeah, though I have tested this at night and I get the same issue. So it still could be the inverters. I don't know. I don't know enough about it, but yeah, so this distortion has nothing to do with what I'm doing, okay? So now I'm going to demonstrate. I will put the unit on with no load. So I'll reset the circuit breaker, and you see the wave that I'm getting, okay? And you can hear, I don't know if you can hear it, but you can hear a hum coming from the isolation transformer. Now if I lower, I change the scale, and now on our 5-volt scale, this is what I'm getting on my switching. Now if I remove the inductive load and I put a resistive load, of course I don't get this. So it's definitely the inductive load is affecting the switching part on the gates. Now, once I start putting a load on, so by the way, at this stage, I'm running the circuit with the 360 ohm resistor on the gate, okay, through the triac. Once I start putting a load, I'm increasing now. So I'll tell you what I'm doing. I'm turning, I've got a load on, okay, up and down, right? And if you see, up and down. So now I've got a load of around 300 milliamps on the inductive load. I'm putting a load on the inductive load, which is about 300 milliamps. Now you're seeing these, still the high peaks there, but the switching is much more closer to, and there it's been tripped, right? Because I've set it only at 300, so I'll put it back on. So the higher the load, okay, hang on a minute. Sorry, because the clip, the prop jumped off, so so that's what I'm getting. Now, I will show you when I will bypass the resistor. So now I'm gonna bypass the 360 ohm resistor, and I get that. So it's a big improvement. Now the voltage drop is to 2.47 RMS, and before was almost 10 volts RMS. Okay, so I removed the Now it's on the 360 ohm resistor. Actually now the voltage drop is 9.17 volt RMS. Now I short circuit the resistor and I get 2.45 RMS voltage drop. Now that's got no load. Now when I increase the load, okay, you can see it improves, right? But if I put back the 360 ohm resistor, there's the peaks. They're much higher. I short circuit the 360 and they come lower. So, showed that. That's the improvement that I have made. So I cannot fit this 360, I have to take it away. And what I'm going to do here, instead of that, being on the circuit board, I'm going to put like a 0.1 ohm fusible resistor. So if something ever happens here, it's like I've got a fuse there, going through the MOC 306 3M. So yes. So the Triac, when I had the Triac running, when I had this type of circuit, okay, I did not experience, with this circuit on, I did not experience that. Now whether because I've got long wires going to the gate and that doesn't help as well, I'm not sure. But almost this was much better because it didn't create that issue. But one thing I do know that this is good. If there's ever a short circuit, this is going to be able to handle the short circuit. Okay? 100 times better than that. So in a short circuit, that's probably going to blow up. In this case, it will not. I've got the fuse, and the fuse should blow up first, the 8 amp fuse. So yes, so that concludes the ending of the explanation to the problem I had with the running the SCR. Okay, and here I'm going to explain sort of roughly the software that I've done for the Variac circuit breaker project. Here the software is done in Pic Basic Pro, okay? So it's not done in Arduino or anything like that. Just have to say regarding Pic Basic Pro that as much as they call it Pic Basic, okay, it's not really that easy when it comes to mathematical calculations. For example, a C compiler like Arduino or professional C compilers like MP Labs or, you know, when you come to work out formulas with maths, it's much easier to do. And because the C compilers normally, they handle a 32 and higher bits calculations, where Pic Basic Pro handles the 230-bit calculation in the chip, but in the software itself cannot do it. They use something like, for example, if you go into help here, they use statements like division 32. Let's see if you could see that. Okay. So I'll have to bring that down. Okay. So this is one of the statements. Pic Basic Pro multiplies times function operates as a 16-bit by 16-bit multiplier, yielding a 32-bit result. However, since the compiler only supports a maximum variable size of 16 bits, access to the result had to happen in 2 steps. So they're giving an example here. They're creating a variable called C and B and A, and then you do, let's say if you're going to do B times A, it returns the lower 16 bits of the multiply, while if you use a times, it return the upper 16 bits. There was no way to access the 32-bit result as a unit. In many cases, it is desirable to be able to divide the entire 32-bit result of the multiply by 16-bit number for averaging or scaling. So you see, here is the flaw, and I'm going to call it a flaw because I don't really care anymore, of Pic Basic Pro. Now I use Pic Basic Pro and it's very good, okay? But again, when you're doing calculations and you want a full 32-bit number or higher, it's a ball breaker. And using the system where if it's a C compiler, you just do whatever you want. Not only that, it handles the points, the C compilers, and same as Arduino software compilers. You can do 3.123 times, 0.02, for example, and it does it for you. Where this will take about probably 5 different steps to do that calculation. You will never get a perfect result, and it's so complex that a lot of people will just give up. So that's one thing Pic Basic Pro should have really, if they want people to use their software, they should have made that as easy as C compilers. Now, C compilers are higher level software that, people think this is more complicated to use. In actual fact, it's easier to use. So this has the rest of the variables, statements. They might be easier than C compilers, but doing microcontroller programming, this thing is not very good. But anyway, I won't say any more about that. I'll continue on here. So here I'm setting up the configuration bits of the microchip. Okay, it's got config 1 and config 2, the 1847, and I'm running this chip at 8 megahertz. Now this chip, I can run it at 32 megahertz, okay, by putting PLL enable on. And reason why I'm not running it at 32 megahertz, okay, because I'm using the analog to digital converter inputs, and you will find if you run it at 32, it will be very unstable, the reading of the analog to digital converters, all right, because the microprocessor is creating more noise within itself. I mean, there is commands there, or microchip advisors to do it in sleep mode and all this stuff. It's just too complicated, and sometimes it doesn't actually work out for you the way you're doing your software. So if you run it at 4, of course, it's even more stable, the analog to digital converter. But 4, I found that it's a bit too slow, for the reason that I'm running an interrupt to read the encoder, rotary encoder, where I set my digits on the LCD screen to show on the LCD screen. I'm setting that, of course, in the microchip. And because depending on how quick you are turning the rotary switch, okay, the faster your processor is running, excuse me, the more you're going to pick up your rotary changes. So if I wasn't using the analog to digital converter inputs, I would run it at 32, and at 32 it's very responsive, and I can turn the rotary encoder very fast, and I will still be able to pick up all the counts of the changes of the pulses of it. Okay, so 8 megahertz I still can, for what I'm doing, it's still good enough. So that's the reason behind it. And here they use a define oscillator rate. That's for the compiler. And I'm using some weak pull-ups for the rotary encoder here. Weak pull-up at B, so it's the Tris B. And anyway, if you program microchips, you would know what these registers are. And I'm not going to spend a lot of time explaining everything, because this is not a video, explaining how to use Pic Basic Pro or anything, or how to program PIC chips or of microchip. But it's just to show what I did for the Variac project. This chip has also got interrupts on a positive edge, and it also can read a negative edge, which is very good. I mean, look, other microchips, high-end ones, they also have that. But a lot of the microchips by microchip do not normally have this. Either they normally would be either positive or negative, okay, edge. But I use both of them to have the rotary encoder more responsive to the interrupt, okay, to pick up the pulses, whether it's gone high or whether it was going on a low. So it's more sensitive. Okay, so Edcon 1, this got to do with right justify is regarding the bits. Anyway, I want to explain that. It's got define here for the compiler regarding the analog to digital bit converter. Depends if you're using the etsyn command, you need this, otherwise you don't need these. But I am using the etsyn command, so these are, whether you're setting the clock source internal, number of bits for the analog to digital converter on the pin, whatever it is, so it's 10, it's a 10-bit. And simply is, again, you got to look at the PDF file of the microchip regarding these settings. This one, ANSEL A or ANSEL B, have to do with whether the input pins, you're setting them up as a digital input or an analog input, as an analog to digital converter, or whether it's going to be just a digital high and a low, okay? So that's what these are. Tris setup's got to do with the outputs. Again, don't really have to explain this. Tris sets your inputs on the chip. So just to explain, whether these inputs are input or a output. So if you're reading a switch or a sensor, it will be an input. If you're switching on a LED or a relay or whatever you're doing with it, then it's going to be an output, of course. So that's what that is. And then I've got for the I2C, I've got a clock pin on port A.2. I've got a data pin on port A.3. So this is the setup configurations, and I'm giving them names here for the setting up a variable for that port and for the channel of the port. And then I'm setting up the rest of the ports, the names, switch ×2. So when I'm pressing a switch to multiply my delay time by 2, that's what that was used for. And I've got a trip pin, and that was used to determine whether the circuit breaker has tripped or it's not tripped. And then I've got the scale pin output, port B.1, and I called it scale pin, and that one, when I'm changing the scale here, so it comes out of pin RB1 and goes through the resistor,
and as you can see here, scale change is going to put on this LED through this chip V01400 AEPT, the one I've used, and it's a dual MOSFET to be able to send both positive wave and negative wave to ground of the scale input. Go back to the software. Okay. And then this is for the analog meter scale. So the times 5 scale, I called it times 05. The times 1 meter x1 and so on, okay, for my scales. Then I am turning those ports on at the beginning of this, when you turn on the power and your circuit board turns on and the microprocessor on the PIC chip boots up, it's gonna turn on all the relays of the scale on. So that's, I don't need this, that's just a visual, just to show that the circuits of the scale are working, and we'll display them on the analog meter LEDs. And then I've got variables here, the names that I've set for the variables. So for example, this is a 1-bit variable because it's var bit. So this will read 0 or 1 only. You know, set switch, set time, set amps. I gave all for my software names. I probably could have used better names. Some of these names they were taken from other projects that I did, and maybe I didn't bother changing the name for it. Okay. This bank 0, this is regarding where those variables are going to be saved. You could save them in different banks. Reason normally this is used because sometimes the interrupt, when you go to an interrupt, not as much as the interrupt system that I'm using. In actual fact, I didn't have to do this. But if I was using not the compiler interrupt, Pic Basic Pro uses 2 types of interrupt. One is set in the compiler, creates an interrupt which makes your code bigger, and the other interrupt is what do you call it now? It hasn't come to me. If I go back to the help, what they call them? Let me just pause it. Yeah, and what I was looking for is the word assembly code, and so the other interrupt is made under the assembler. Okay, which what happens is in most cases the program will jumps to the start and might corrupt some of your variables. Okay, so then you might want to store certain variables in bank 0. Normally when you go to an interrupt, this bank doesn't get corrupted, and that's why any variables that you don't want, you want to keep, that you're not going to be resetting during your code working, it is advised to store them in different banks, like bank 0. So that's what that is. I actually don't need that in there because I'm not using assembly interrupt system. The assembly interrupt system, in most probably C compilers, that's what they use. But Pic Basic Pro, again, it might sound like they're making it easier for you to have a compiler it does it in the compiler, which means it adds extra code when it compiles it for an interrupt. The only problem with that is that it takes a couple of steps longer, and also, if you use a pause command, for example, if let's say you do pause 1000, which means you're pausing your code for 1000 milliseconds, which is 1 second. It means your interrupt will be delayed for 1 second. That is laughable. Now, I'm again sort of criticizing, a Pic Basic Pro, but why did they do it like that? You know what I mean? Why couldn't have they made their compiler that it doesn't do that? So everybody else doesn't do that. So C doesn't do that. So then you need to do it in assembly if you don't want that to happen, because assembly will not read your code. It will not read whatever you've written on your code when your software is running in the chip on the program counter, and it will bypass that. So if you put a pause, it's still gonna ignore the pause. And how I said, that's your code running, for example, here. Let's say your main code. Where are we? Let's say starts here, main. You call it whatever name you want, of course. It adds, you don't see it, but once it compiles it, it adds each line. It's gonna add an extra line of code to go to an interrupt. So first it needs to read that line, then it will go to the interrupt. So if you have a pause here, okay, so for example, where am I using a pause? Let's say I'm using pause 1, that's 1 millisecond, okay? It's gonna read this. Even there's an interrupt flag already on the chip, okay, on the register. It's not gonna execute that until it came out of the pause, because the interrupt is done here underneath. You don't see it, but when you compile it, it creates a number of files, Pic Basic Pro, and then on those files you can see it, how it will add an interrupt here, line. This is how actually I'm running it. You think, well, why are you running it like that then, if you're criticizing it? Because Pic Basic Pro, it's complicated to write your code in assembly, okay? Not because they're making it easier for you. That's actually a lie. They're not making it easier for you, okay? What it is, the way they've written it, okay, it sounds like for the rest of the stuff it's easier than C, but it's not, because, how I said, if you're using interrupts, okay, to do it like the C, how C would do it, right? The compiling I'm talking about, not the way you write the code. The way you write the code, you write it in C. You're not doing any extra stuff for it to do an interrupt. It's still handled by the compiler once you compile it. Then, to do this on a professional level by using assembly, then it's too complicated and it's harder than C. I have done it in the past, and I have written it under assembly, okay? And that's because people have put examples on the internet, which I thank them for that, okay? People like, unfortunately has passed away, and he helped a lot of the people on Pic Basic Pro forum. Why is it that where are we here? Daryl Taylor, okay? Sorry that I forgot his name, it couldn't come to me. Daryl Taylor was a professional programmer, okay, from what I know. A very good, nice guy. He done heaps of coding and helped a lot of people, okay? Unfortunately, he did, pass away. So God bless his soul. And for example, Pic Basic Pro, later on I realized that you can have include files, which I've learned this on my own, trial and error type of thing, watching examples and stuff like that. I did have a book that I bought, so you can add include files. So Daryl Taylor, I'm using one of Daryl Taylor include files here to run the parallel to serial chip PCF 8574A that connects to your LCD screen, alphanumeric, to make it run on I2C instead of running parallel with extra wires, which means you need to use more ports on your chip. He uses assembly code, and he was very good, and you can create your own statement sort of in a way through assembly. I have created some of my own include files looking at Daryl Taylor, but mine are very simple, and they're not as sophisticated as Daryl Taylor's, because mine, the reason why I included made my own include files, so it makes it easier to understand and not too much code on your main page. But I don't include assembly files on my include files, okay? So I've created two include files here, one 12C setup, I called it, okay, and one MCP 4725, and that was to run the deck, to be able to communicate with the deck down here, MCP 4725, and I created my own include file and my own software. In actual fact, I haven't seen no examples of on the internet under Pic Basic Pro. Heaps of stuff for Arduinos and other things, but of course Pic Basic Pro is left behind because no one's interested in it anymore. But because I've started with that before Arduino was around and all that, and I got used to this, to use it, and I'm sort of stuck with it. I never moved away from it. So yes, it is good, but it has some negative things when it comes to what I was saying. Interrupts mathematical calculations. It's not very good when you consider what Arduino or C compilers can do. And that's why professionals do not use this, because of that reason. And I have talked to one particular professional guy about it. So this is my include file that I created for the deck, which I've learned from Daryl Taylor, how to sort of do it. Learn from his code, and I've done my own code to be able to talk to the deck, and this was all my idea how I done it. It probably can be done better. I'm not a professional, okay? I've just learned on my own, and that's all it is. So I can include this in the main code, and I don't have to have an include file, okay? Now I like to say something regarding Arduino, okay? Arduino, again, it has negatives too, and I'm going to tell you what the negatives are. I like to see all the coding, because when I'm working out something, I like to be in charge, number one, of understanding of how everything is working. Now the problem with Arduino, okay, and they still haven't done this, the problem with Arduino, they don't show you the include files. Yes, you can go and try manually trying to find them, but their platform of the software environment to program, on the side, let's say on the side here, you can't find your files. They're not in. They haven't created this thing, and they've done that on purpose. Okay, now. The purpose is not to help people, okay? And you think, why are you saying that? Because if they really wanted to help people, you help people by making them understand everything, not half a job. So everybody on Arduino, half the people that program, do not really understand everything. I mean, I don't understand. I'm not claiming that I understand everything, okay? What I'm trying to say is that a lot of the code and sketches, they call them, okay? They give examples, and then people use that, and they can do their project very easy and quickly. That's what have they created, right? But whenever you want to change something that it's not in your sketch, a lot of people do not know how to do that. And the environment of the software is not really letting you change that. You have to go manually find the files, the hidden files, after you included them in your software, and see how, trying to work out how they done it. But they don't, no one is there to explain that. So there's professional people creating those codes that they understand from, you know, A to Z. That's good, they're very smart, but they don't almost, to me, it's like they don't want everybody to become like them. So whether it's because it will become too complex for the beginner, but why not have it, why not say, I'm gonna give an idea here, if somebody wants to take that on from the Arduino people. In actual fact, I don't even use Arduino, right? But why don't they have this software where you can have it basic and you can have an advanced button? And for a beginner, you'll have it under basic and it doesn't include the rest of the other files. And for the advanced person, can have it under advanced, and then you can see your other files. So you can change those files if you want to modify the code to run in a different way, okay? Instead of waiting for someone else to do it and then let's update, give it an update, and there's been a revision of that particular sketch, okay? So I'm not being smart, I just don't like how you don't have that environment where you could do that. Because I have used, for example, other software, okay, where, let's see if I have it here. For example, Keel. So you see, for example, this is C programming, and this is I used the Nordic chip for some projects that I did. You see the environment here of the software shows all the other files. .h, they're called like perimeters, whatever, include files. You can go to them and you've got the whole, everything that's running in your code. Then you got one called main C, which is standard under C. And there's your files. Why don't they make Arduino like this? Is it because they don't want you to be able to do it under professional? Is that the reason why? Huh? Because there's many reasons, I suppose, to why they will not do it like that. Okay? But all I'm saying, if you want the people to learn, you give them all the tools, mate. You know what I mean? Not half. So I'll continue on because I think I've wasted enough time with that on my code. Okay?